Chapter 3: Stream Classification. The greatest challenge for one who is experienced in understanding the processes and combined complexities of rivers is to effectively communicate with those who are not. Dave Rosgen. Introduction. Each stream reach segment of a stream is unique, and the form it takes is governed by the processes flowing through it over time. The stream is, in effect, constantly solving complex hydraulic and sediment transport equations with an ever-changing set of interrelated input variables, making form adjustments where necessary through erosion and deposition. These equations are based on the laws of physics, yet are too complex to solve, even if all the correct inputs could be obtained. Classifying streams provides a framework for understanding stream complexity. Classification serves many purposes: describing, assessing, identifying, treating, monitoring, and discussing similar streams in consistent ways, and is an essential aid to effective communication. In everyday conversation, we routinely classify and group objects based on their similarities. This helps us to understand each other, but an understanding can be no clearer than the definitions by which the objects are grouped. If we describe the same type of thing in the same way and then use the same terminology consistently, we greatly improve communication, i.e., we each know what the other is talking about. The geomorphological, hydrological, and ecological characteristics of a stream change many times from its headwaters to its final destination. Reaches of a channel differ depending on the functions each performs and the constraints placed on them by the valleys through which they flow. Therefore, each individual stream reach is given a classification. Describing stream reaches discretely, uniformly, and consistently, while clearly accounting for a wide range of variables, is conceptually difficult. Yet, classification is essential if we are to talk about the same types of streams in the same way. As each stream reach is unique, so are the characteristics of streams flowing through the Southwest landscape as compared to streams in more humid environments. Therefore, streams flowing through these dry lands have additional characteristics that need to be considered when classifying their reaches. In the practice of induced meandering, it is important to classify a stream reach correctly, because some channel types qualify for treatment while others do not. Similar stream reaches will tend to respond similarly to the same kind of treatment. A treatment that would be appropriate for one stream type might not be appropriate for another. Classifying a stream reach is best done on the ground with visual observations and data collection. A brief outline for conducting a stream survey is presented at the end of the chapter. The induced meandering stream restoration method is based on the precept that stream channels evolve predictably from channel type to channel type and follow well-documented scenarios or progressions, if certain conditions are met and there is sufficient time for predictable change to occur. Setting a realistic restoration goal depends on having a clear understanding of what channel type is the proper and reasonable type for that environmental setting. By determining the channel type, a baseline is established from which to measure change. When the project reach is monitored following treatment, one can assess whether or not management goals are being attained. Morphological classification. Since form and function are linked in these dynamic systems, studying the form, determining if the form is stable, and classifying streams by their form accounts for much of their behavior. By using a morphological stream classification system, and then basing restoration treatments on the appropriate stable form, the best connection to the natural system will be maintained. In nature, there is no preferred stream type. When there is sufficient water flowing in a stream channel, it is constantly self-adjusting towards equilibrium with the natural vegetation, flows, and sediment regime of its valley. It is people who classify streams and who may tend to prefer one type over another. In restoring a stream, it is important to avoid the pitfall of trying to force-fit a stream to a type that is not appropriate for its valley or present watershed conditions just because that type might be most appealing. Morphological classification ensures that treatments are appropriate to the scale and form of each stream reach and not a one-size-fits-all attempt. Morphological classification makes it easier to understand how different stream processes function, helps to pinpoint problem areas, and reduce variability for departure and stability analysis. Morphological monitoring documents how the stream form changes over time, providing the essential data for determining stream channel stability and for determining if the stream is progressing toward greater or lesser stability. The Rosgen Stream Classification System. The Stream Channel Classification System, developed by Dr. David Rosgen, is based on fluvial processes in which form follows function in maintaining a stream channel. For over 44 years, Dr. Rosgen and his associates have measured and monitored thousands of streams of every type all over the United States. The Rosgen Classification System, used by most federal and state land management agencies in the U.S., represents a quantum increase in our understanding of stream channel processes. Dr. Rosgen teaches, ask a critic, what model do you use to predict the depth and slope of a glide? No analytical approach will generate the answer. The only known method is to measure a reference reach of the same stream type in the same valley type. Regime equations are notoriously inaccurate, often having a 200 to 300% variation in the width to depth ratio. The fundamental feature of the Rosgen system is the bank-full concept, in which the form and dimensions of the active channel and its associated floodplain at bankful discharge are used as the stream's vital statistics. As discussed in Chapter 2, the bulk of stream bank erosion and sediment transport work over time is performed by discharges at or close to bankful discharge. Therefore, the Rosgen system classifies streams by the forms they create when they are conveying water, transporting sediment, and dissipating energy.
Figure 3-1, 3-2.
The bank-full concept reveals how the river assimilates channel-forming forces over time. For the student, it can be difficult at first to identify bankful features, since it is unlikely that the stream will be flowing at bankful discharge on the day of observation.
Photo 2-11, page 28.
With a bit of experience, however, the ability to identify bankful becomes the most powerful skill that the restoration practitioner will use to understand river stability, channel-forming processes, and behavior. River stability is defined as a river or stream's ability in the present climate to transport the stream flows and sediment of its watershed over time in such a manner that the channel maintains its dimension, pattern, and profile without aggrading or degrading. Aggradation is a raising of local base level due to sediment depositional processes, whereas degradation is a lowering of local base level due to channel incision processes. Rosgen, 2008. For the reader to gain an understanding of stream channel types and natural stream channel evolution, the authors have condensed the basics of this information from Rosgen. There are 4 assessment levels in the Rosgen classification protocol. This book only covers levels 1 and 2 in detail. For more information, refer to Dr. Rosgen's Applied River Morphology, 1996, and River Stability Field Guide, 2008. Stream classification applies to a stream reach, not the entire stream. A reach is a continuous segment of a stream channel that has the same channel dimensions, meander pattern, and slope. A bioreach is a stream reach with the same plant community. Throughout this book, stream channel classifications apply to reaches or bioreaches of a channel rather than to entire rivers. A Level 1 assessment describes the geomorphic characteristics that result from the interaction of basin relief, landform, and valley types. It is the broad identification of corresponding major stream types. It begins with looking at the valley type and knowing what stream channel types the valley is likely to support. Many of the survey criteria, such as valley type, slope, channel pattern, and watershed size, can be determined from topographic maps, satellite imagery, and aerial photographs. Level 1 also provides a framework for organizing river information. Rosgen, 1996, 1998. Level 2 assessment provides a morphological description of a stream reach that requires a basic stream channel survey, including a longitudinal profile, cross-section, plan view, and particle size analysis. This level characterizes bankful features, the width of the floodplain in relation to the stream channel width, sediment supply, and basic stream stability issues. The Rosgen Level 2 classification is explained more fully in the following pages. A Level 3 assessment looks at existing stream conditions, departure from their potential, and the prediction of stability. At this level, a detailed analysis of channel stability is completed. The assessment applies various methods for analyzing the influence of riparian vegetation, bank erodibility, bank stress exerted by high flows, sediment supply, and sediment transport. Permanent cross-sections, bank erosion pins, and scour chains are installed so that even small changes in the channel can be accurately measured in the future. A Level 3 assessment is beyond the scope of this book. A Level 4 assessment, field data verification, is accomplished through detailed monitoring. Streams are resurveyed after bankful events to evaluate predictions of stability made during the Level 3 assessment. Velocity and sediment transport can also be measured during flood events to validate and calibrate mathematical models. Level 3 and 4 surveys are required for successful restoration or stabilization projects on large or complex rivers. Rosgen Level 1 Survey Assessment, Reading the Landscape. A Level 1 survey includes looking at structural controls, lithology, fluvial processes, depositional materials, climatic influence, broad life zones, basin relief, landforms, valley morphology, and drainage network patterns. Valley types. A valley can be formed by plate tectonics, glaciation, flowing water, or a combination thereof. Its shape often depends to a large extent on the characteristics of the stream that flows through it. Rivers with steep gradients, as in mountain ranges, produce valleys with steep walls and a narrow valley bottom. Shallower slopes in general produce broader and gentler valleys with narrow floodplains. But in the lowest stretch of a river, where it approaches its base level, such as the sea, it begins to deposit sediment and the valley bottom accommodates a broad floodplain. Based on constraints and mutual interactions, stream channel types fit the valley type in which they are found.
Figure 3-3.
Please refer to Appendix B, Representative Valley Types of the Southwest, on page 186 for photos and descriptions of how the 11 basic valley types are expressed in this region. Channel types. In Level 1, streams are classified as A through G types based on visual assessment alone. The Those experienced in the Rosgen classification system can do the Level 1 classification from a moving vehicle without taking measurements. Sometimes classification can be done from topographic maps, photos, and satellite imagery. It is helpful for beginners to go through the Level 2 survey process to gain the skills needed to quickly and easily perform a Level 1 classification. Therefore, a more in-depth description of a Rosgen Level 2 survey follows. Rosgen Level 2 survey and classification. For a Level 2 assessment, it is necessary to conduct a physical survey of the stream channel, measuring the dimensions that will be used to classify the stream, including entrenchment ratio, width to depth ratio, sinuosity, and slope. In addition, the average particle size in the channel bed is calculated from a statistical survey of channel bed materials. All of this information is based on Bankfull stage. A short section on field survey methods is located at the end of this chapter, including a discussion on identifying Bankfull stage. Entrenchment ratio. The entrenchment ratio, ER, is the first and most important criterion in the Rosgen classification system. The entrenchment ratio compares the width of the Bankfull channel to the width that the water surface would have during a standard flood. This ratio is a critical diagnostic for energy dissipation, stability, and stream channel evolution. The entrenchment ratio is measured across a straight portion of the stream at the top of a riffle, because this is where the width of the water surface most significantly affects energy dissipation during overbank floods. The standard flood used to compute this ratio is the hypothetical flood that would be exactly twice the height of the Bankfull stage. To be precise, several terms must be introduced before the entrenchment ratio can be properly defined and visualized.
Figure 3-4.
Bankfull maximum depth, D max, is defined when the stream is flowing at Bankfull stage as the depth of the deepest point, Thalweg, in the stream channel at a riffle cross-section. The flood-prone width is defined as the calculated width of the water surface if the stream were flowing at exactly twice Bankfull maximum depth. Note that this standard flood and its associated width is not to be confused with any type of flood danger zone. It is an arbitrary definition that fluvial geomorphologists use for standardized comparisons. To determine the flood-prone width on a graph of a riffle cross-section, measure how wide the water surface would be if the stream were flowing twice as deep as Bankfull maximum depth. To compute the entrenchment ratio, the flood-prone width is divided by the Bankfull width. The larger the ratio, the more access the stream has to its floodplain when it overtops its banks. At the low end, natural channels eroded through bedrock or gullies forming in deep alluvium may have an entrenchment ratio as low as 1.0, no floodplain at all. A stable meandering channel flowing through a broad, gently sloping alluvial valley would have an entrenchment ratio of 2.2 or greater. In this landform, large floods have room to overtop stream banks and dissipate energy flowing relatively shallowly through floodplain vegetation. A rectangular concrete channel would have an entrenchment ratio of 1 because the flood-prone area would be identical in width to the Bankfull channel.
Figure 3-5.
A typical trapezoidal channel would have an entrenchment ratio slightly larger than 1. At the high end, natural channels in some landforms can have entrenchment ratios exceeding 100, i.e., the floodplain is 100 times as wide as the Bankfull channel. Refer to Figure 3-1, key to the Rosgen classification of natural rivers chart on page 44 for the following discussion. In the Roskin stream channel classification system, a B stream type has an entrenchment ratio between 1.4 and 2.2. Streams with less floodplain access than a B stream type are called entrenched streams. These are the F and G stream types. These and some A and B stream types are the only ones appropriate for induced meandering. The single-channel streams with more floodplain than a B stream type are the C and E stream types, which can be the channel type goal of an induced meandering project. Applying induced meandering to C and E stream types would probably do more harm than good. Width to depth ratio. The width to depth ratio, W/D, of the bankful channel is the second most important criterion for classifying and understanding a stream. It is measured at a riffle cross-section and defined as the bankful width of the water surface at bankful stage, divided by bankful mean depth. Bankful mean depth is a calculated value obtained by dividing the bankful cross-sectional area by the bankful width.
Figure 3-6.
Width to depth ratio is then calculated by dividing bankful width by bankful mean depth. Note that mean depth is used here as opposed to maximum depth. Width to depth ratio is what governs the distribution of shear stress and sediment transport within the bankful channel. The normal range for this ratio is between 1/2 and 150. Classification example part 1. The single thread stream channel has an entrenchment ratio of 2.3 and a width to depth ratio of 29. Therefore, the channel could be a C or E type. Refer to figure 3-1. Sinuosity. Sinuosity, K, is the wiggle factor. It is the ratio of channel length to valley length.
Figure 3-7.
An artificially straightened stream would have a sinuosity of 1.0 because the stream length would equal the valley length. In a naturally meandering stream, the channel length will be somewhat longer than the straight line valley distance. Since every meander is different, this is best analyzed by examining a stream reach long enough to include several typical meanders. Let the starting point A be where the stream is heading straight down the valley on the outside of a bend. Let the end point B be several meanders downstream on the outside of another bend that bends the same way.
Figure 3-7.
The channel length is the curving distance along the center line of the bankful channel from point A to point B. The valley length is the straight line distance from A to B. To calculate sinuosity, divide channel length by valley length. Sinuosity varies by stream type. It is less than 1.15 in most ephemeral channels, including most gullies. A stable meandering stream with a floodplain has a sinuosity from 1.15 to 2 or higher. For ephemeral streams in the drylands provinces, a sinuosity of 1.3 is considered high because there is usually not sufficient riparian vegetation to armor the banks against erosion during bankful and greater floods, which tend to straighten the channel. Sinuosity is important because it affects channel slope and the ability to erode and transport sediment. Induced meandering directly increases the sinuosity of a stream channel. Classification example part 2. The stream has an entrenchment ratio of 2.3, a width to depth ratio of 29, and a sinuosity of 1.25. The channel can now be classified as a C stream type. Slope. Stream channel slope, S, can be measured from the top of a riffle to the top of the next downstream riffle, or it could be measured over a long distance encompassing several riffles. This is calculated by the rise over run formula.
Figure 3-8.
The elevation difference between the tops of two adjacent riffles is divided by the stream channel length between them. Increasing sinuosity through induced meandering will decrease stream channel slope. Classification example, part 3. The stream has an entrenchment ratio of 2.3, a width to depth ratio of 29, a sinuosity of 1.25, and a slope of 1.8%. The channel is still classified as a C stream type as opposed to a CB, 2% to 4% slope, or a CC, slope less than 0.1%. Channel bed material. The size of the particles making up the stream channel bottom, figure 3-9, governs the forces required to transport them and therefore maintain the stream channel morphology over time. Larger particles protrude into the flow and affect the hydraulic roughness of the channel. A simple statistical analysis of 100 stratified particle samples taken from the bankful channel, called a pebble count, is used to determine the distribution of particle sizes. The samples are apportioned between all the bed features, riffles, runs, pools, and glides when conducting the count. The average particle size is called the D50. This is the diameter larger than 50% of other particles. Figure 3-9 provides a visual representation of particle size by class. Classification example, part 4. The stream has an entrenchment ratio of 2.3, a width to depth ratio of 29, a sinuosity of 1.25, and a slope of 1.8%. A particle count reveals that the D50 of our stream is 75 millimeters. Cobble. This makes the stream a C3. Other designations. Stream types can be further stratified to account for steeper or more gradual channel slopes where the slope is out of range of the norm for that stream type. This can communicate the evolutionary history of a stream. For this designation, a lowercase letter is added to the stream type letter. For example, a BC stream has an entrenchment ratio, floodplain access ratio, of a B stream. For example, a BC stream has an entrenchment ratio, floodplain access ratio, of a B stream, but has the gentler slope of a C stream type. Perhaps a BC stream has recently incised and lost access to its floodplain.
3 designators, lowercase a, b, and c, are used to mean the following. Refer to figure 3-1, page 44, for more examples. A. The stream slope is considered much steeper than other streams of this type. The AA plus stream type is steeper than 10% slope, the maximum slope of the normal A stream type. B. The stream slope is somewhat steeper than other streams of this type. The EB stream type is steeper than 4% slope, the normal maximum slope of the normal E stream type. C. The stream slope is more gentle than other streams of this type. The BC stream type has less than a 2% slope, the normal minimum slope of a normal B stream type. Please refer to Appendix C for photos and description for some representative stream types of the Southwest. For a full complement of stream and valley type photos, refer to Rosgin's Applied River Morphology, 1996.
Dryland streams are different. What are drylands streams? Drylands are typically defined as areas of the world where potential average yearly moisture loss, evapotranspiration, exceeds average yearly moisture gain, precipitation. Evapotranspiration is the combined measurement of water loss to evaporation and transpiration. Transpiration is the loss of moisture from plants to the air via the stomata within their leaves. 47.2% of the Earth's land surface is dry land. Normal dry seasons can last 6 months or more. Droughts can last for years. Lancaster, 2006. A dryland stream is a watercourse that drains these arid lands if and when the rain comes in earnest. Curiously, the rarely occurring extreme flood events in dryland streams tend to be much more severe than corresponding events in humid lands. The 50-year flood in the San Juan Mountains of Colorado, or a high precipitation mountain range in Idaho, might be 4 to 5 times bankful discharge. In the arid Southwest, it is likely to be 15 to 20 times bankful discharge. This results in lower stability for dryland stream channels. Stable dryland stream channels compared to streams in more humid regions tend to be wider and less sinuous, reflecting the reduced effectiveness of stream bank vegetation in stabilizing the banks. There is a higher proportion of marginally stable stream reaches in the drylands, and many of these can become deep, unstable gullies in response to poor land management practices that impact watershed conditions. If the instability results in channel incision, these streams are likely candidates for induced meandering, but treatment is only worthwhile if the initial cause of instability is also addressed. Dryland rivers have a difficult time flowing to their destinations because of sparse rainfall, thirsty aquifers, and urban and agricultural uses, including evaporation from reservoirs. The Rio Grande's flow does not increase as it moves down the state of New Mexico, and the Gila River does not reach the Colorado River as it once did. Evaporative loss. Another important loss of water in the drylands is from evaporation. According to an article by hydrologist William M. Turner in the September 25, 2003 Albuquerque Journal, studies conducted by the state engineer, the Interstate Stream Commission, Bureau of Reclamation, Army Corps of Engineers, and water scientists show that annual open reservoir water loss due to evaporation is up to 591,000 acre-feet. The article also states, currently, annual municipal and industrial water usage for the entire state of New Mexico is only 195,000 acre-feet. Turner, 2003. People like to see the exposed water surface of a reservoir and think that it is creating a supply of water. Unfortunately, reservoirs in the desert Southwest function more like evaporation ponds. Hydrologists have calculated that open reservoirs in hot, arid regions exposed to wind and sun can have evaporative losses of 6 to 10 feet per year. Small ponds are often the main source of drinking water for grazing livestock. The Natural Resource Conservation Service, NRCS, in Douglas, Arizona, estimates that evaporation from dirt livestock watering impoundments amounts to 10 feet per year. Evaporation from these stock ponds account for 64% of the total water lost annually, while seepage, cattle consumption, and transpiration accounting for 31%, 3%, and 2% respectively. Dusterhouse, 2008. Perhaps a more reliable place to store water would be in groundwater aquifers, where it is protected from evaporation but less immediately available than water stored in above-ground reservoirs. Transmission loss. An important difference between ephemeral streams and perennial streams is the amount of transmission loss. There is substantial transmission loss when an advancing flood pulse encounters porous alluvium on the dry channel bottom of an ephemeral stream. Except in the case of a flash flood, the water must first soak into the ground to some extent before the surface flow can be supported. In fact, an ephemeral dryland stream is continuously losing water during brief flow events as water seeps into its bed and banks. If the flow duration is long enough and the alluvium is porous enough, water from the stream can percolate down to the groundwater table in some places, thus recharging it. It can take a substantial volume of water to saturate a stream bed in order to facilitate surface flow along many miles of dryland stream. Therefore, a stream's bankful discharge does not necessarily increase as it flows down valley, invalidating the regional curve concept. Dryland streams have a very large continuum of conditions. Local channel morphology and the location, size, geology, and runoff from tributaries determine typical flows. During a recent flood on the Santa Fe River in New Mexico, the front of the flood advanced over the dry river bottom very slowly as the water soaked into the ground. According to Dr. Jerry Jacoby, the Santa Fe Preserve, below the Santa Fe Wastewater Treatment Plant discharge, is 1.5 miles long by approximately 50 yards wide and is full of native trees planted by wild earth guardians. This area was observed as a functioning floodplain wetland during a recent runoff event. During the early evening of August 4, 2008, a major flood of approximately 300 plus CFS spilled over the concrete grade check dam at the lower end of San Ysidro Park below Caja del Oro Grant Road, perhaps 2 to 3 miles upstream from the preserve. The uncontrolled flow entering the upper end of the preserve was quickly dissipated by the branching and anastomosing channels throughout the riparian vegetation and soil of the floodplain. It took several hours before 100 CFS finally emerged in the river channel at the lower end of the preserve, followed by diminished flows throughout the following days. The floodplain captured an unnaturally high flow, compounded by lack of sufficient infiltration surfaces upstream, then slowly released it downstream. This was most likely a combination of transmission loss and channel storage. Karst geologic formations, which are not unique to drylands streams, can also complicate and exacerbate transmission loss. Because creeks in karst topography lose discharge to cracks and cavities in the limestone, these leaky watersheds are always exceptions to the regional curves. Photo 3-1. Cedro Creek drains a 19.5 square mile watershed as it flows over karst topography in the mountains east of Albuquerque. According to the regional curve, figured 2-8, page 29, it should have a cross-sectional area of 20 square feet, yet stream channel cross-sections measured in the field consistently come up with a bankful cross-section area of only 14 square feet. Cedro, 2009. The bankful channel is smaller because 1/3 of the discharge flows into the cavities in the limestone and enters the aquifer instead of flowing down the stream channel. The dominance of bankful discharge in dry lands. The link between bankful discharge, stream flowing near top of banks, and effective discharge, discharge at which the most channel shaping is done over time, can be tenuous in dryland streams. The return interval for bankful discharge can be numerically computed for stream gauge data. Bear in mind that this is only an average. Inconsistent rainfall in drylands cause channel-forming flood events to occur at such irregular intervals that other channel-forming processes often intervene in the meantime. The dominance of the bankful discharge as a channel-maintaining agent is challenged in the drylands by alternating droughts and floods that often create cyclic disequilibrium. Droughts kill bank-protecting vegetation, while massive floods pummel the vegetation with stones, uproot the vegetation, and cause excessive erosion.
Photo 3-2.
The relative magnitude of a 25-year flood as compared to a bankful flow is much greater in a drylands stream than a similar humid lands stream. Knighton, 1998. Graf, 2002. Moody, 2003. A large flood in a drylands stream has a greater capacity to radically alter the channel form. Large floods flow across terraces where sparse uplands vegetation provides meager surface protection. It is not unheard of for a 50-year event to flood over and cut through the second terrace, carving the stream a new channel in several hours. This would not happen in a humid region where a 50-year event is unlikely to be this high, and even if it were, the terraces are well protected with lush vegetation supported by the higher rainfall. Flood and drought regimes cause channel instability, while a moderate weather regime allows for the slow re-establishment of bank-stabilizing vegetation in the intervening years. In an ephemeral stream, vegetation growth can also occur in the dry channel bottom between large flood events, often mitigating headcut or bank erosion. Depending on the chance location of this vegetation, it could also partially block the flow during a runoff event, causing severe bank erosion and sometimes leading to channel avulsion, although this is not very likely. In a human land stream, bankful discharge does a good job of characterizing the stream's overall behavior because the flood frequency graph has a relatively narrow peak before diminishing to an insignificant value. However, in drylands, the influence of infrequent extreme floods is not an insignificant factor on channel and valley morphology. Discussions of flood frequency and flow duration of ephemeral dryland streams have to be site-specific. Flow characteristics vary widely. There are ephemeral streams in Death Valley and Owens Valley, California that flow once every 50 years, and ephemeral streams in Kansas that flow 20 times a year. At the time of publication, there are no available paired data sets of flood frequency and sediment transport for drylands ephemeral streams in Arizona or New Mexico. If these data were collected for a particular stream, it could be graphed using the same methods as Woolman and Miller, 1960. Therefore, based on the discussion above, the authors hypothesize what the graph might look like. Figure 3-10, page 54. The effective discharge in the drylands may turn out to be a broad band of discharges, starting at bankful discharge. A more complete analysis of the drylands' effective discharge would account for the sparseness of drylands vegetation, higher sediment loads, and extreme floods. Will the real Thalweg please stand up? The dry bed of an ephemeral channel is at a higher elevation than when bed load is mobilized during a runoff event. The cross-sectional area at bankful is therefore greater than would be calculated by performing a cross-section of the dry channel or when the channel is at base flow. When the stream is dry or flowing at base flow, the vast majority of the sediment capable of being mobilized is at rest on the channel bed. The effect is more pronounced in silt and sand bed channels due to the potential for greater scour depth. To be accurately repeatable, the Roskin Level 2 assessment protocol measures the dry or base flow channel bed elevations. Bear in mind, however, the roots located beneath the channel bed are a better indication of bed elevation during a runoff event in a drylands ephemeral channel. On the Rio Puerco, because of siltation on the channel bottom, when the river starts to run dry, the wet channel has a larger capacity than the dry channel. Therefore, vanes in the Rio Puerco were installed with the tip of the upstream post several inches under the dry surface of the bed, photo 3-3. In this way, the post vane would be at the proper elevation to perform its hydraulic function during a bankful event, chapter 5. An arroyo flows through time. As one example, a C5B arroyo near the Continental Divide in southwest New Mexico has a watershed area of 2 square miles, photo 6-4, page 133. One reach of this arroyo has been observed for 18 years. It had at one time reached equilibrium, long after the watershed was destabilized by grazing, woodcutting, levees, and a highway culvert 1/2 mile downstream that was set too low. The normally dry arroyo may flow up several times per year for days to weeks at a time, yet may not flow at all for 2 years. Twice during the 18-year period, it has maintained a base flow for 6 months. The stream did not flow at all during 2003 to 2004. Then the monsoon season of 2005 started with 3 bankful events that beautifully shaped the banks and supersaturated the alluvium. Unfortunately, these flows were followed by an extremely large flood that overtopped and cut through the second terrace, where sparse rabbit brush and grandma grass vegetation were no match for the scouring force. The flood cut off a meander and sent a 2-foot head cut 200 feet upstream, where it was stopped by the roots of a large juniper tree. In 2006, the arroyo flowed 13 times, about 5 of which were at or near bankful. The juniper roots have become slightly abraded, but are still strong. Eventually, a moderate climate regime may persist long enough for a new floodplain to form in the degraded reach and for tree and shrub roots to effectively knit the channel bed and banks together again. At that point, the system will become stable. In the meantime, willows, cottonwoods, and seep willows have been planted to stabilize key spots within the meander pattern. Seasonality of flood events. There are important differences between winter storms and summer monsoonal events. Winter events are often region-wide and can affect a large watershed, while summer monsoonal flood events, thunderstorms, typically fall on small areas of 1 to 5 square miles, producing localized flow in small tributaries with little effect on the main stem stream. It can take a lot of accumulated precipitation to saturate a large dry lands watershed, overcome transmission loss, and produce a bankful event. This can be accomplished by massive regional winter storms and tropical depressions. Early in the monsoon season, summer thunderstorms initiate flashy stream flow in small tributaries, which may or may not be sufficient to create flow in the receiving stream. As the monsoons continue, a buildup of ground moisture may facilitate stream flow, although the seasonal increase in grass and forbs in the uplands will start to utilize part of this moisture. The aerial extent of a monsoonal thundershower has to overlap a drainage basin to maximize stream discharge. A squall moving from upstream to downstream can also add to peak discharge. Therefore, each storm produces a unique discharge based on intensity, duration, antecedent moisture, vegetation ground cover, basin overlap, and squall path. During Arizona and New Mexico summers, a weather forecast of 20% chance of rain could mean a near 100% chance of rain in the area, but only a 20% chance that it will rain in a particular small watershed. A flash flood in a tributary can plug the main stem stream with sediment, causing a temporary pond, resulting in eventual avulsions or head cutting. In some cases, the sediment plug can become colonized with vegetation, raise the stream grade, and form riverine wetlands. Historically, when a system became degraded by a catastrophic natural flood event, restabilization would depend on the chance occurrence of a long and moderate weather regime. This might take a century to occur, and the system would be susceptible to disequilibrium for a long time during the healing process. The author's experience suggests that once watershed stability is reestablished in a dryland system, its stability is sustainable. This can be attributed to a long growing season and the hammock effect provided by roots of streamside vegetation. The hammock effect. In ephemeral dryland streams, the channel may have surface flow for only a few hours or days per year. While the channel appears dry, there can still be water present just beneath the surface that vegetation can utilize. If the water table is high enough to be tapped, it is common for tree roots to weave in great profusion under the channel bed. This web of shallow horizontal tree roots provides a solid matrix where riparian plants, such as deer grass, can securely anchor themselves to the channel bed. In effect, the channel rests on a fabric of woven roots, hence the term hammock. Photo 3-4. This association of species forms a guild because the grass protects the tree roots from abrasion, and the combination of grasses and trees effectively armors the banks and holds the soil in place, allowing both grass plants and trees to thrive in a high-energy environment. During a flood, water and sediment flow in the channel over and through this vegetation. Various combinations of vegetative armoring of bed and banks can have a beneficial impact on the stability of dryland streams by reducing overall scour and taking advantage of short flow durations and long recovery intervals between floods. Emery oaks and junipers in an ephemeral desert channel can act like cottonwoods, stabilizing the bed and banks with their roots. Very large roots of a willow, cottonwood, or juniper will act like a bedrock sill, effectively preventing a headcut from migrating upstream. Photo 3-5. Protecting the integrity of the hammock is important for maintaining landform and ecosystem stability. Cutting streamside trees or killing the grass with excessive grazing will directly rupture the hammock, as will abrasion from excess sediment supply, livestock trampling, or vehicle traffic. If their root systems weaken, the trees may die. Degradation of the watershed can weaken trees when the hydro period is drastically shortened, which in turn can cause the hammock to weaken and tear. Cienagas, wetlands unique to the desert. A ciénaga is a riverine wetland in the drylands that forms a sheet flow valley bottom. At mid-elevations of 1,000 to 2,000 meters in semi-desert grassland, and more seldom in Madrean evergreen woodland, a certain marshland community is associated with perennial springs and headwater streams. These warm temperature habitats were most often termed ciénagas, cien aguas, or 100 waters, by Hispanic and later explorers and settlers and appear distinctive. Ciénagas are perpetuated by permanent, scarcely fluctuating sources of water, yet are rarely subjected to harsh winter conditions. They are near enough to headwaters that the probability of scouring from flood is minimal. The system is controlled by permanently saturated hydrosoils, within which reducing conditions preclude colonization by any but specialized organisms. Hendrickson, 1984. Ciénagas are populated by semi-aquatic sedges, rushes, and some grasses. Photo 3-6. They support very shallow, braided channels tending toward sheet flow wet meadows between deep pools. Photo 3-7. Pools are situated near trees and have vertical walls of organic sediments and undercuts below root systems. Trees are scarce, limited to those that can tolerate saturated soils, such as Gooding willow. Immediate surroundings are sometimes rendered saline through capillary action and evapotranspiration. These areas are populated by halophytes, salt-tolerant species. Extensive stands of saccaton grass are also common on adjacent flatlands. Ciénagas are plant communities that develop in southwestern desert streams where shallow bedrock forces permanent groundwater to intersect the surface and where the stream power is slightly less than the power required to transport the sediment load. Slowing of runoff across very wide floodplains with low gradients is essential to ciénaga formation. In these special places, a nearly year-long growing season promotes rapid invasion of saturated stream beds and arroyos by vascular hydrophytes, wetland sod, and consequential initiation of organic deposition during periods of flow stability. As organic materials accumulate, Water levels rise accordingly through flow impedance, capillarity, and other water-holding attributes of the spongy detritus itself. This can cause permanent riparian vegetation to become established along a very wide swath, much wider than the typical stream channel for a comparably sized watershed. This, in combination with dampening and net attenuation of flood pulses by increased infiltration and water storage in saturated soils, enables the system to cross a stability threshold. Flooding of a magnitude sufficient to scour the bed of all other stream types passes over well-developed cienagas with little damage. Although possessing tremendous stability, cienagas also have a certain fragility and are susceptible to rapidly expanding erosion if the surface is scarred by anthropogenic disturbances such as livestock overgrazing, livestock trailing, poorly drained roads, or anything that creates concentrated flow and initiates gully formation. Road culverts have ruined many a cienaga, as has livestock trailing. A sudden change in the volume, direction, or concentration of water flowing across a cienega can start a gully, for example, by diverting channelized flow from a road ditch across its surface. Another sure way to destroy a cienega is to degrade the watershed above, causing a blanket of coarse textured sediment to be deposited on the cienega surface, which can lead to colonization by upland species. Cienagas act as self-protecting water storage reservoirs. Flows downstream from cienagas are less variable and of greater permanence than flows in streams lacking cienagas. The large amount of storage capacity and slow release of water dampens and attenuates flood peaks. As such, cienagas create downstream conditions conducive to the establishment of riparian vegetation. Further downstream expansion of the cienega is expected, yet eventually becomes limited as the supply of fine textured sediment is trapped in the wetland above. Upstream expansion of cienagas occurs as channel width increases due to aggradation and reduced competence, causing deposition of clays and silts. These clays may form impervious layers that perch the water table and expand the wetland. Cienagas somewhat violate climax concepts. Specifically, as deposition occurs in cienagas, they advance up valley at a slope less than the slope of the valley in which they form. This increases the gradient at the downstream end of the landform, which causes an increase in velocity, which in turn can initiate a cycle of erosion of the toe. Bull, 1997. This accounts for the alternating cienega and arroyo formations described by early travelers to the desert southwest. Palynological evidence showing deep accumulations of organic sediments deposited in cienagas and exposed in contemporary arroyo walls provides testimony for long-term persistence, greater than 4,000 years, of individual cienagas with rare cycles of incision and rebuilding. Once gullied, cienagas are unlikely to self-restore using natural processes because the sediment supply may continue to be trapped in the sod filter of the terrace, starving the gully of the sediment it needs to refill itself. Over the years, agricultural practices have reduced the number of cienagas throughout the desert southwest. What few cienagas remain in properly functioning conditions serve as tiny islands of unique habitat, providing refungia for many species incapable of surviving in vast expanses of a desertified landscape. Among rapidly disappearing aquatic habitats of the Southwest, a few cienagas have an excellent potential for perpetuation and should be given a high priority as a unique remnant of our natural heritage. Perpetuation of cienega habitats will require maintenance of groundwater and a balance between aggradation and denudation. Ideal restoration treatments will restore sheet flow to the historic landform, induce bank and channel storage, and reconnect flowing groundwater with the cienega surface. The authors propose adapting the Rosgen stream classification system to include cienagas as stream type DA, figure 3-11. Techniques of field survey. This section is included as a brief outline. A detailed study of the book Stream Channel Reference Sites, an illustrated guide to field technique by Haralson et al., 1994, is required reading for anyone who lacks prior training in stream channel survey. This publication is available online at www.treesearch.fs.pubs/2073. Channel Morphology Datasheet. The Channel Morphology Datasheet for Stream Classification, Appendix D, page 192, can be used as a field worksheet for information and data collected during a Rosgen Level 2 field survey. The datasheet was adapted from Rosgen's book Field Guide for Stream Classification, 1998. Research, mapping, and calculations. Before taking to the field, take to the files. Haralson et al., 1994. Find out and document what geomorphic data have been collected in your area. Review sources on regional climate, geology, land types, vegetation, etc. Do a bit of map work prior to conducting a stream channel survey. Paper maps spread out on a large table or even the floor are preferable to viewing this information on a small computer screen. Don't get lost in cyberspace. Procure a U.S. Geological Survey 7.5-minute topographic map of the watershed. It may be necessary to tape several maps together to view the entire watershed. Trace the watershed divide with a pencil. Estimate the watershed area and the watershed areas of significant tributaries. The watershed area is then used to determine expected bankful width, bankful depth, and bankful cross-sectional area from the regional curve. Moody, 2003. These values should be entered on the survey sheet before going to the field. This often helps resolve which bank is the bankful feature in the field. Utilize the internet. Google Earth is a useful resource which can be downloaded free. http://www.googleearth.com. This software and associated database allow the user to zoom in on a satellite view of the water planet using software tools provided. In areas that have good resolution, it is possible to estimate valley slopes, sinuosity, meander lengths, etc. These estimates are not accurate enough for design, but are a good way to help prepare for a site assessment. In the field. Draw a site map in the field notebook from Direct Observation, figure 3-12, page 60. Taking the time to sit on a high point and sketch a map is important because it will allow one to gain an understanding of the spatial relationships of important features. The site map should include direction, arrow, scale, legend, natural landmarks, stream channel features, riffles, pools, bends, significant boulders or bedrock, eroding banks, large trees, artificial structures such as fences, houses, etc. Modify the map as fieldwork continues. Bankful indicators. Bankful discharge, ED, is defined as that water discharged when stream water just begins to overflow onto the active floodplain. The active floodplain, ED, is defined as a flat area adjacent to the channel constructed by the river and overflowed by the river at a recurrence interval of 2 years or less. Luna Leopold quote from Woolman and Leopold, 1957. Bankfull is a depositional feature as opposed to an erosional one. This is a critical point. Any surfaces that are eroding would not be reliable candidates for determining the Bankfull stage. The variety of physical and visual indicators of the Bankfull stage that enables field determination of Bankfull include a floodplain at a stage that roughly corresponds to the cross-sectional area from the regional curve, a surface associated with the top of the point bars, convex change in slope from a sloped bank to a relatively horizontal surface, even if this surface is very narrow, a break in slope of the banks and/or a change in particle size distribution of bank materials, evidence of inundation feature such as small benches, staining of rocks, exposed roots below an intact soil layer, distinct break in density or type of vegetation, change in bank materials, either fine or coarser, bank undercuts, lower limit of lichen growth. An excellent learning tool and valuable resource for identifying Bankfull in the field is the U.S. Forest Service video, A Guide for Field Identification of Bankfull Stage in the Western United States, featuring Luna Leopold, http://stream.fs.fed.us/videos.html. Prior to conducting the longitudinal profile survey, slowly walk the reach to be surveyed, identifying Bankfull candidate surfaces where they exist on both banks all along the channel. Place pin flags at these locations to make sure that they will be surveyed during the longitudinal profile. When they are graphed on the same coordinate axis as the thalweg, water surface, and terraces, it should become apparent if there is consistency in identifying the Bankfull waterline, which should be roughly parallel with the water surface, if there is base flow. The difficulty with determining Bankfull. Correctly determining Bankfull features in the field can be one of the most challenging tasks in dryland's fluvial geomorphology. Training in this procedure or consultation with a reputable practitioner of the geomorphic method is recommended. In this region, so many stream networks are in a state of evolutionary change initiated by historic land use that it is often prohibitively difficult or impossible to find a stable stream reach. As Roskin has noted, recent channel changes may give false indications of Bankfull. If the stream is not stable, identifying Bankfull is difficult, if not impossible. There may be no meaningful Bankfull morphology. The channel morphology will indicate something else instead, like the intensity of the last major flood. In these unstable dryland systems, it is often puzzling to compare candidates for Bankfull from one cross-section to another because they may not agree. Many G and F channels in ephemeral systems have no discernible floodplain. In G and often in F channels, the toes of both terraces are often scoured during a large storm, preventing the formation of a floodplain depositional feature until the gully bottom becomes wide enough for floodplain development. It may, therefore, be impossible to determine Bankfull in these situations. In such cases, hike both upstream and downstream of the reach and look for identifiable Bankfull features in a relatively stable, non-incised reach. Survey this reach as well and use its data for a template to restore the impacted reach. If there is no stable reference reach nearby, broaden the search, looking for a stable reach in the same valley type with a similar particle distribution. If this cannot be found, the regional curve is the final option. For small watersheds under 10 square miles or so, it is acceptable to use the regional curve to derive a bankful cross-sectional area for the purpose of induced meandering design calculations. This is discussed in Chapter 7. Surveying basics. A basic field survey establishes the horizontal and vertical location of a series of points in relation to a starting point called a benchmark. A Level 2 assessment requires a longitudinal profile, plan view, and cross-section surveys, which are discussed in the following sections. Survey data should record the relative position of stream channel features with sufficient precision to document changes. This type of survey is best done with at least 2 people. Harrelson et al. 1994. Minimum equipment includes surveyor's level or laser level and tripod, leveling rod, several 300-foot tapes used for cross-section and longitudinal profile, field notebook, wood survey stakes, rebar stakes, camera, GPS unit or hand compass, channel morphology datasheet, Appendix D, page 197. Establish a benchmark as the initial reference or starting point of the survey. Locate it on a permanent natural feature outside the channel and outside the floodplain if possible, yet near enough to be clearly visible. The top of a large immovable boulder is ideal. Longitudinal profile survey. The longitudinal profile, which should be completed before any stream cross-section, produces a graph illustrating how the stream channel changes elevation as it goes downstream. See Figure 2-14, page 39. During the longitudinal survey, the bankful determination is made and the locations and facet slopes of channel features are accurately determined. Variables derived from the longitudinal profile survey include water surface and valley slope, elevation of bankful relative to the channel bottom or the water surface if there is water flowing, bed features such as pools, riffles, and head cuts, channel length, locations for cross-sections just below top of riffle. The station in the longitudinal profile is used to locate all stream channel features, cross-sections, etc. A measuring tape is laid out along the center line of the bankful channel. 4 lines are tracked at each station during this survey: thalweg, water surface if there is water in the channel at the time of the survey, bankful, and terrace. Each point is recorded and graphed in a field notebook before the survey instrument is moved. Not only does this provide an instant illustration of the channel morphology, it also allows for errors to be corrected before leaving the site. It is important not to wait until you get back to the office to plot your data and discover or permanently record an error.
Figure 3-13.
Plan view survey. This is the bird's eye view of the channel meanders and other features. It can be done in detail with a sub-meter GPS, Figure 3-14. If this equipment is not available, sufficient information can be gathered concurrently with the longitudinal profile by recording the compass bearing to each successive point in the channel. When plotted with protractor and pencil or by a computer, sinuosity and the locations of bends, riffles, etc. can be displayed. The Mecklenburg Reference Reach spreadsheet has a module that will do this. The original sketch map can be redrawn on top of this plot to improve the accuracy of this sketch. Alternatively, a large-scale aerial photograph or satellite imagery may be used as a base map on which to plot channel features. Cross-section survey. A stream channel cross-section is measured perpendicular to the direction of bankful stream flow. Base flow may be flowing in a slightly different direction due to local curves in the thalweg. The riffle cross-section is the basis for determining channel form in the Level 2 assessment. Other cross-sections can be taken of runs, pools, glides, eroding banks, or point bars, but the riffle cross-section is used to determine the essential variables for a Level 2 classification. Variables derived from a cross-section survey, Figure 3-15, include bankful width, bankful mean depth, bankful maximum depth, flood-prone width, entrenchment ratio, width to depth ratio. The riffle sections and bankful features are identified during the longitudinal profile survey. Choose a representative cross-section of the surveyed reach. Do not locate a cross-section where the character of the channel changes. A relatively straight riffle between two meander bends that has clearly identifiable bankful features is an ideal location for a cross-section. The cross-section should be just downstream from the top of a riffle, not directly at a break in the channel slope or near any abrupt changes in channel shape, size, or obstructions, such as a large boulder or embedded log. Since the standard graphical representation of a stream channel cross-section is looking downstream, the tape is stretched across the channel with the zero end on the river left side. This is best accomplished with two people so that the cross-section can be aligned to be level as well as perpendicular to the bankful stream channel alignment. It must also cross the thalweg at the cross-section station determined during the longitudinal profile. The tape should be long enough to include the entire flood-prone area in the cross-section. If there are overflow channels, an old channel cut into the terrace, or other interesting morphology, it is informative to include these in the cross-section as well. When the alignment of the tape is suitable, stakes are pounded at both ends of the cross-section and the tape is stretched tightly between them. The cross-section should be monumented concurrently with the benchmark before survey measurements begin. Record the station in the longitudinal profile where the tapes cross, and consider naming the cross-section accordingly, such as XS-12220, photo 3-8. Measure elevations starting at the river left stake, which should be station 0 on the tape. Shoot an elevation at each break of slope so that the data will accurately model the stream cross-section, paying attention to facet slopes. Record the station of each measurement to the nearest tenth of a foot. Vertical precision should be 1/100th of a foot. Avoid features such as stumps, flood debris, or the pits of small potholes that might cause spikes on the graph. Check each point to see if it is representative of the stream's morphology a few feet upstream and downstream of the cross-section. Always record the edges of the water surface if there is water in the channel. Establish photo points looking at the entire cross-section from upstream, downstream, and across the channel. Take the photos with the cross-section tape in place. This will make it easier to do photo retakes and to compare the photos to the cross-section graph. Channel bed material, pebble count. The composition of the stream bed is an important facet of stream character, influencing channel form and hydraulics, erosion rates, sediment supply, and other parameters. Restoration strategies and applicable in-stream structures vary according to channel bed material. The Woolman Pebble Count 1954 is the most efficient technique for determining an estimate of particle size distribution. This survey requires one person to wade in the stream or walk in the arroyo to measure particle size, while another person records data. Particles are tallied using Wentworth size classes, in which the size doubles with each class. Figure 3-16, 3-17. The output of the pebble count is the distribution of particle sizes available to the stream for erosion, transport, and deposition. A field datasheet for recording the particle size distribution can be found in Appendix D, page 198. For small-grained particles, use a sand gauge, Appendix J, page 217. Display of data. When graphing a stream channel longitudinal profile or cross-section, using a vertical exaggeration of 10 by 1 will make the often subtle stream bed features more obvious. However, relying exclusively on the vertical exaggeration tends to be misleading. The authors recommend using both vertical exaggeration and true representation to get the best understanding of the data. If graphing and calculating by hand, be aware that counting squares to determine cross-section area is only valid on a 1 by 1 graph format. Linear left brains struggle to understand a three-dimensional stream channel shape by looking at three two-dimensional diagrams: the longitudinal profile, cross-section, and plan view. The authors recommend putting them in the same scale and juxtaposing them in one large-scale diagram to facilitate a holistic understanding of the channel morphology. Figure 3-18, page 65. Data calculations. Mathematics is a tool that helps us analyze the consequences of our assumptions and values, yet it is we, and not some mathematical divinity, who determine the assumptions and values. Paulos, 2001. There are spreadsheet tools and computer programs available on the World Wide Web for analyzing survey data. The Reference Reach spreadsheet, developed by Mecklenburg and Ward, 2004, is a tool for river evaluation, assessment, and monitoring. Embedded in the spreadsheets are details on the equations and theory that are used to generate the reported outputs. The modules include 1. Reference Reach spreadsheet for reducing channel survey data and calculating basic bankful hydraulic characteristics. 2. Regime equations for determining the dimensions of typical channel form. 3. Meander pattern module that draws the meanders of the centerline of the bankful channel from the longitudinal survey data. 4. Cross-section and profile sediment equations that include expanded and condensed forms of critical dimensionless shear, boundary roughness, and common bed load equations. And 5. Contrasting channels that compute hydraulic and bed load characteristics in a side-by-side comparison of two channels of different user-defined forms. Interpretation of the survey data. Sometimes field measurements will not agree with regional curves. This can be due to transmission loss, geology, upstream impoundments and water diversions, or recent channel adjustments from a large flood event. It may take both a check of available data and a careful reading of the landscape to determine the cause of the disagreement. For example, near Huatros, New Mexico, the Mora River has developed a well-defined depositional surface that resembles a bankful bench. The regional curve and stream gauge data revealed that, due to effective irrigation diversions in the snowmelt system, the river has flowed at bankful level only once in 7 years. The bankful candidate that looked so promising was actually a well-developed inner berm. If applied in an urbanized watershed, the regional curve will predict a discharge that is too low. In an urban setting, with large amounts of impervious surfaces, the flood crest will be higher than in a rural setting, with a corresponding increase in the bankful cross-sectional area. Summary. Streams are classified in order to define and describe stream complexities in a consistent manner. This facilitates communication between interested persons. Classification of rivers aids in understanding how rivers are similar how they differ, and how they function. The Rosgen classification of natural rivers provides a basis for consistently differentiating between channel types. The Rosgen methods for surveying stream reaches and acquiring the information necessary to describe channel types at the level 1 and level 2 intensities were presented in this chapter. An understanding of surveying methods and the classification system is essential to planning, designing, implementing, and monitoring stream restoration projects. Because dryland streams are different from humid region streams, some important aspects were discussed for the benefit of practitioners undertaking the design and implementation of restoration projects affecting dryland streams.